Hello my dear students, I am Divyam and I am welcoming you all in my another video of the topic hybridization by valence bond theory. This topic is taken from the chapter number 9 coordination compounds. In this video we are going to discuss about the calculation, or you can say that to find out the hybridization by using valence bond theory. So for this you should keep in mind the following points. To find out hybridization by valence bond theory, we should remember the following points. So what are all the points here? You should know about the coordination number, which is related to hybridization, and shape here. So if the coordination number is 4, that means if you have a metal here and you have a ligand having 4 in number, so the hybridization will be sp3 and the shape will be tetrahedral. Okay, if the coordination number is 4, that means if this is taking up the d orbital also. What does this mean? That let's say if we have the d orbital of metal, an s orbital of metal, and p, this means that we are taking this d, 1d, 1s and 3p, and if we are having dsp2 hybridization, the shape will be square planar. Okay, if the coordination number is 6, there is two possibility again. That should be, or that would be, outer orbital complex or inner orbital complex. What does this mean, outer and inner? This is outer and this is inner complex. This means that the d orbital which is used in the hybridization is of inside of d orbital. That means let's say we have 3d, 4s and 4p. So the d orbital used here is this. That's why it is known as inner orbital complex. And if the d orbital used is 4s, 4p and 4d, that means this is outer complex here. Okay, but both have the shape of octahedral. So this you should remember this point, that if we have coordination number 4, we have two possibility, and if we have coordination number 6, we are having two possibilities again. Okay, the next point you should remember is that we should know the atomic number and oxidation number of central metal atom or ion. You have to remember the periodic table from 1 to 30, and for an exceptional, you should know the atomic number and oxidation state of platinum, palladium. That's it. Okay, so first of all you have to remember the periodic table till 30, and you should know the electronic configuration also. Okay, the next point is ligands. About ligands, ligands are of two type: strong and weak field ligand. Okay, strong field ligand and weak field ligand. That means if there is a strong field ligand, the splitting energy, the delta naught, is very high. It means this will leads to pairing. This will leads to what? Pairing. Okay, and delta naught is very high. And what is delta naught? Delta naught is the energy gap between these two orbitals. Okay, this is the energy gap between these two d orbitals. Okay, so strong field ligand, it means the delta naught is very high, pairing will be possible here. If there is a weak ligand, the delta naught is very low and there is less chances of less pairing possibility. Okay, so let's say we have this particular example of FeCN whole 6 4 negative. As you can see here, this 6 represents the coordination number. This 6 represents the coordination number, and 6, it can be D2sp3 or S p3d2. As we had already seen, there is two possibilities here. It either a inner orbital or outer orbital complex. So let's have a look here, that if we have iron and the sphere is having -4 charge, first of all you have to calculate the oxidation state or oxidation number of iron here. So for that you have to do a small calculation, that x, if we want to calculate the oxidation number of iron, so it is x, 6 multiplied by -1 is equals to -4. So it is -6 is equals to -4. Then x is equals to +2. So iron is here in +2 oxidation state. As you can see here, +2 oxidation state. That means this 2 electrons is going or releasing here from here, and this has 4s 0. Okay. So now 3D is having 6 electrons, 1, 2, 3, 4, 5 and 6. Okay. Now, as we know, the Cn is a strong field ligand. Okay. Cn is a strong field ligand. You can learn a small trick, that if the ligand starts from C, N or P, this forms a strong ligand. Okay. If the ligands form a bond having carbon or nitrogen or phosphorus, that ligand is a strong field ligand. And if the bond formed in between ligand and metal by oxygen, halides and sulfur, then the ligand categorized as weak field ligand. Okay, here this is strong field ligand. You have to learn this. Okay, if the bond is formed by in between metal and ligand by carbon, nitrogen or phosphorus, then that ligand is a strong field ligand. Okay, and that will cause pairing. You can check my previous video also, so you will understand this particular thing. Okay, so Cn is a strong field ligand. It will pair up all the electrons from here and it forms like this. Now the 3d orbital of iron having 2 vacant orbitals here. Okay, 2 vacant orbital. 4s is already vacant because this is now in 2+ oxidation state, and 4p is also vacant. So the Cn will donate its electron pair here and form a octahedral complex. Okay, 1, 2, 3, 4, 5 and 6. So what is the hybridization here possibly? It is dsp3. D why D? Because it is taking up inner orbital. Inner why? Because it's taking up the d orbital of one less, third d shell, not 4d. Okay, here it is taking up 3d. So the hybridization is d2sp3. The shape is octahedral. It is diamagnetic because all the electrons are paired up. If one electron is also left without pairing, then that compound will be paramagnetic. So you have to check that all the electrons should be paired, then only that compound is diamagnetic. And it is low spin because all the electrons are paired up. Okay, I hope this is clear from here, that how you will deduce the hybridization you have by using valence bond theory. You should know about weak field and strong field ligands, and also you should know about the shape, that is which coordination number represent which shape. You should know that. You have to learn it first. Now let's discuss about some limitations of valence bond theory. There I had point out 6 limitations here. So you can take a screenshot from here, or just let us understand all the 6 points here. It involves large number of assumptions, as we had seen that we have to assume that why we had no particular logic behind why the carbon, nitrogen or phosphorus ligands are strong in nature, or why some ligands are weak in nature. We have to also assume that it's a point charge. These all are the assumptions, okay, we are taking. It does not give quantitative interpretation of magnetic data. It always say that this compound is this compound is paramagnetic, but we had not seen the quantitative. We are not calculating the magnetic moment here. It does not explain the color exhibited by coordination compounds. We also does not explain here the color exhibition, why this compound is purple, this compound is pink, that kind of thing. It does not explain thermal or kinetic stability of the compound. It does not deals about the stability of coordination compound. No exact prediction can be made about the shape of the complexes having 4. Coordination number 4 represents two types of shape. One is square planar, and one is tetrahedral. Okay, and square planar is having sp2, dsp2, and tetrahedral sp3. No exact prediction can be made about. By just seeing the coordination number 4, we can't tell that that compound is square planar or tetrahedral. So here is also a confusion. It creates confusion here. It does not distinguish between weak and strong field ligand. We have to just mug up that this ligand is strong and that ligand is weak. So all these are the limitations of valence bond theory. That's why crystal field theory comes into picture, to just ruled out or come across to clarify all these things. We are now studying the crystal field theory. So in CFT, you have to study crystal field splitting in octahedral coordination entities and tetrahedral coordination entities. You have to study octahedral coordination entities and tetrahedral coordination entities. So as you had already studied the d orbital structures in class 11, just here you can quick recall all the orbital diagrams here, that dxy, the orbitals, the lobes in x and y axis in between. In dxy, the lobes are in between the x and y axis, and d orbitals, as you know, it's double dumbbelled. Okay, the dxz, it means the two lobes. The lobe is present in between one lobe, and two lobe is present in x and z, so it named as dxz. Here you can see the lobes are present in y and z axis, that's why the name is dyz. Here it's on the axis x and y. On the axis x and y, the lobes are present on the axis. You should remember that dx square minus y square and dz square, the axes are on the axis, the lobes are on the axis. In these two, the lobes are on the axis, and in these three, the lobes are in between the axis. You should remember this. Okay, now let's study the orbital diagram. You had studied orbital diagram. Let's now just a quick recall of this splitting energy diagram. Here you can see the orbitals are in higher energy levels. This is the metal d orbital when there is no ligand. When there is ligand approaching, it comes, the orbital gains some energy, and then it splits into two. Okay, the dxy, dxz and dyz get a lower energy by 2/5, and this gets 3/5 higher energy. Okay, why this happen is, if the ligand approaches, and ligand always approaches by an axis. Okay, so if the ligand approaches from the axis, here it is not getting interact with any lobe here, because the lobes are present in between the axis. In between the two axes, the lobes are present, and the lobes are the places where the electron we can find. There is a probability of finding electrons always inside the lobes. Okay, so the ligand's electron does not interact with the electrons present inside the lobe. That's why the energy of dxy, dxz and dyz is lower as compared to these two. In case of this, if the ligand approaches from the axis, it interacts with the electron present inside the lobe. That's why these two orbital gets higher energy when the ligand interact with central metal atom. That's why the orbital gets a higher energy, dx square minus y square and dz square. Okay, here in diagram you can see, and this difference is known as delta naught, the crystal field splitting energy, delta naught. This is a barycenter. You can see here, this orbital is known as T2G and this is EG. Okay, so in writing the electronic configuration, you have to remember that these three orbitals are named as T2G and these two orbitals are named as EG. Okay, so now the next is the crystal field splitting in tetrahedral coordination entities. But before that, we have to know about delta naught also. So delta naught depends upon the ligand and charge on metal ion. The ligand and the charge on metal ion. In ligand, we are going to study the two categories, strong field ligand and weak field ligand. As I had already told you how you can distinguish between strong and weak field ligands. Okay, so based on the nature of ligands, we can write electronic configuration of d orbital of central metal atom. This type of question has been asked in your examination, so be prepared by practicing many questions like this. So if you have D4, we have two possibilities of electronic configuration. It may be possible that the electron reside 1, 2, 3 and 4. This is one possibility, and the other possibility is the electron may be 1, 2, 3 and 4. So if this case is here, it means this one, and if this case we are dealing, so the electronic configuration of this is like this: T2G4 EG0. This is EG and this is T2G. Okay, so why in which condition we are going to attain these kind of electronic configuration? Let's quick recall here that if we have this condition, delta naught is less than P. Delta naught is less than P. That means, let's say, if we have this, and in this case the delta naught is high, it means the crystal field splitting energy is high here. Okay. Okay. 1, 2, 3 and 4. 1, 2, 3 and 4. If the splitting energy is less, there is chance of electron to jump into EG orbital. But if this gap is very much high, the fourth electron will reside here. This electron is not going to jump in the higher energy level. Okay, so if delta naught is higher, pairing occur and complex is low spin, and it happens in the case of strong field ligand. Okay, and this happens in case of weak field ligand. No pairing occur, as you can see, and the complex is high spin. So it's very much important to understand this. And you have to practice this type of question, that if it's d4, then what will be the configuration in both the two conditions? If it's d5, which type of configuration you will get? So you have to practice this by your own. So now let's understand the crystal field splitting of tetrahedral entities. In tetrahedral, what happens? Same as it's a d orbital free metal ion, it's a free metal, and when ligand approaches, it acquires little bit higher energy. It's a higher energy, and then it splits into two. But in this case, there is a opposite kind of thing you can see here. In this, the dx square minus y square and dz square attain lower energy as compared to these three. This is a reverse case of octahedral. And also you can see here we are writing just E, not EG. And here you can see we are writing T2, not T2G. So in this case, in tetrahedral case, the electronic configuration you will write as T2 and E. That cannot be T2G and EG in case of tetrahedral. So keep in mind this. Now, same as this is barycenter. And this difference in this two energy, to orbital energy is delta T. Here delta T. And in octahedral case, there is delta O, delta naught. Okay. Here you can observe that delta T is equals to 4 by 9 delta naught, or you can see delta T is equals to 0.44 delta naught. You have to learn this. Okay. So let's say we have to write the electronic configuration in tetrahedral. So if it's a D5 configuration, it's an example. If you have a D5 and delta T is higher than delta P, delta T is higher means delta T means this gap is very much high. This gap is very much high. So electron will reside in the lower energy, and that electron will not go upside. That means pairing occur. If delta T is high, pairing will occur. If pairing will occur, the D5 electrons, most of the electron, that means 1, 2, 3, 4, 4 electron will be here in E orbitals. Okay. So here you can see if delta T is high, there is pairing occurs, and complex ion is low spin. Low spin means most of the electrons are paired up and strong field. Okay, and the configuration is E4 T2 1. But if the delta T is less, the electron will jump in the higher energy orbital, and the electronic configuration will be E2 T2 3. Okay. So you should know these kind of electronic configuration. It's very easy to write the electronic configuration in this as compared to you had already studied in class 11th. So just you have to make sure that you are studying each and every point in this chapter, and you will definitely score better. So as we discussed in this video, the crystal field splitting energy of tetrahedral, octahedral, and also the valence bond theory, and to calculate the hybridization also. So now some limitations of crystal field theory is also there, and that's why ligand field theory come into picture. So let's have an idea of the limitations here. The first limitation is the assumptions that the interaction between metal ligand is purely electrostatic and cannot be said to be very realistic. Not all the metal ligand is purely electrostatic. Okay, so it's an assumption that we are dealing with the assumption. The second is this theory takes only d orbitals of a central metal atom into, and the s and p orbitals are not considered to be studied. As you had seen that we always taking the d orbital of central metal atom, not s, not p. Okay. The third is The theory fails to explain the behavior of certain metal which causes large splitting while the other shows small splitting. Let's, for example, H2O is a strong ligand as compared to OH. In the both cases, the oxygen is making bond with the central metal atom, but H2O is little bit stronger as compared to OH negative. The ligand crystal field theory has not explained this type of confusion, so it's a limitation. The fourth is the theory rules out the possibility of having p bonding, and this is the serious drawback because it found in many complexes. It only discuss about the d orbital pairing. Okay, and also the last one is no significance to the orbital of ligand. We are only dealing with the orbitals of central metal atom and not of the ligand's orbital. So these all are the limitations of crystal field theory. Just take a screenshot of this and you have to remember this. It can be asked in your examination. So here we are going to end this video. If you had studied and understood some of the things very clearly, so just like my video and share, subscribe also, and comment also if you want me to make another video on some topic. So just let me know. Thank you all for watching.